All right. Good morning, everyone. So we're going to finish the cycloaddition chapter today, and then we're going to move into the second type of pericyclic reactions that we'll be talking about, the electrocyclizations. So as the last part of the cycloaddition chapter, I just want to cover one type essentially of reaction that we have seen before. It deals with oxidations of double bonds, and this is specifically covered here as part of this chapter because the first step in this reaction falls under the category of a 1,3 dipolar cycloaddition. So in your book, this is 24.7 and 24.8. It deals with the cleavage of diols. So now the reason that we cover this under the chapter of cycloadditions is that the first critical step that generates the diol is essentially a 1,3 dipolar cycloaddition. And the classical example for a reaction like this deals with, for example, cyclohexene as the starting material. And we use a catalytic amount of an oxidant, and this is osmium tetroxide. So usually this is used catalytically because osmium tetroxide is very, very toxic, and you should use the minimum amount necessary to run your reaction. This can be recycled inside the reaction flask by adding a stoichiometric oxidant, and this is usually hydrogen peroxide, so H2O2, and that's the stoichiometric oxidant. And then you usually run this in a mixture of water and acetonitrile, let's see, CH3CN. And what this generates is a diol, and it's a syn or cis diol in this case. So you generate basically from the double bond two hydroxyl groups. And these two are, with respect to each other, that's the critical factor for this bishydroxylation, that they are cis with respect to each other, or syn if you're talking about acyclic structure. Now, I mentioned that the first step in this reaction that leads to this bishydroxylation is going to be a pericyclic reaction, and we can look a little bit closer at the mechanism. And let's say we have our cyclohexene over here, and then we can draw osmium tetroxide just next to it. So osmium tetroxide looks something like this, with 4 oxygens, and this undergoes a 4+2 1,3 dipolar cycloaddition, where you can take basically the electrons from this bond, move them over here. You can take these electrons, move them over here, and take these electrons and move them towards the osmium. And that will give us as an intermediate an osmate ester. I can draw this out. And the fact that it's a pericyclic reaction defines essentially the stereochemistry around this osmate ester. So that guarantees essentially that these hydroxyl groups are going to end up on the same side. So you have an oxygen here, and then your osmium, O, and this is your osmate ester. And I can draw the stereochemistry in here. So the hydrogens at these positions go towards the back. And then if you turn this reaction over, so you basically hydrolyze this osmate ester, H2O, you're generating the reduced species of the osmium. So this is then osmium 6, OH, and this can then be recycled with H2O2 to osmium tetroxide. again. So basically this is the oxidation, again, to regenerate your catalytic amount of the osmium tetroxide. Now, what we get out of this reaction after hydrolyzing this osmate ester is, of course, the diol. And here you see clearly that the stereochemistry that we had introduced through this 1,3-dipolar cycloaddition is reflected in the stereochemistry of the hydroxyl groups in the product. So again, here we have the syn stereochemistry, and that is basically translated into the product. Now, osmium tetroxide is not the only reagent that you can use to perform this reaction. And oftentimes there is like this, this interaction between using something that is as toxic as osmium tetroxide if you could get away with a less toxic reagent. It's manageable, but the problem with other alternative reagents is that they're often not as nicely selective as this osmium tetroxide reaction. So the same mechanism, you can actually perform it with potassium permanganate. Same reaction with KMnO4. And this would be, at a first glance, like a very viable alternative to the reaction with osmium tetroxide, because this is significantly less toxic than osmium tetroxide. The problem is that in order to control the reaction with potassium permanganate, you have to have a very, very tight control over the temperature of this reaction. So if we have, for example, a cyclic double bond like this, and we use stoichiometric amounts of potassium permanganate, so we're not using catalytic amounts here, and then we have to use a base, sodium hydroxide, and usually this is done in water as a solvent. We still do the same kind of 1,3-dipolar cycloaddition here that leads to the syn ester. So manganese here, and then we have oxygen and O, negative charge here. And then we have, of course, the countercharge of this is the potassium. If we have the temperature under control, we can hydrolyze this. So if we have OH minus here, and we get the hydrolysis, then we can be successful at getting the bis-hydroxylated product that we so desire. However, if the temperature is just a little bit higher than 25 degrees, and please keep in mind that this is an exothermal reaction, so it's a little bit iffy to control and keep at exact a precise temperature. So let's say T larger than 25 degrees Celsius, then usually what happens is that with the stoichiometric amount of potassium permanganate that you have present, you further oxidize this first to the bisaldehyde. So you break the carbon-carbon bond. And then with additional stoichiometric potassium permanganate that floats around in the reaction mixture, this goes directly to the diacid. And this is usually then the thermodynamic minimum of the reaction. So COOH, COOH. So it's critical for these reactions to control the temperature, and it's not that easy because this first step already is exothermal. So you're generating heat that warms up the reaction, facilitates this side reaction here that leads to the undesired product. So that's why often in these systems we use osmium tetroxide, even though it is a pretty nasty reagent. So selectivity here again is syn in this case. All right, so just to complete the story of the geminal, the diols, the syn diols in this case, I just want to talk about one last reagent that basically acts upon diols that look a little bit like this. And that allows you to basically access a mode to cleave this bond here selectively to access, for example, the aldehydes. And those are pair iodates. So pair iodate mediated CC cleavage. So what you need in order for this to work is that you need a diol, and it doesn't always have to be syn, but it has to be able to adapt a conformation where you can form a per iodate, a cyclic per iodate ester. So let's pick one simple example here. Let's say we have a T-butyl group over here. And in this case, we're going to use a trans diol. I'm just going to show you in a little bit later why this is relevant. But what the pair iodate essentially does, it recognizes these two alcohols essentially as functional groups that it can form an ester with. So if you mix this with per iodate, so that's HiO4. So this is either the free acid, or you can use the sodium or the potassium salt. Both of them work. But what you generate is essentially an inorganic ester of this. How did we have the stereochemistry here? Okay, so O, and then O, and then you have your iodine here, and then you still have O and one OH over here. And this is essentially, we call this a per iodate ester. Per iodate ester, right? And this in itself can now cleave, and you can basically draw these arrows out if you want to. So the idea is we want to cleave this carbon-carbon bond here. If you think about this as a retro 1,3 dipolar cycloaddition, that's what you essentially get out of this. So you end up with then the bisaldehyde here, and the stereochemistry up here stays the same. And as a side product, you generate the reduced form of the iodate reagent, right? Now, the important part for this reaction to work is that you actually have these hydroxyl groups here in a conformation where they allow the formation of this cyclic iodate ester. And not all reagents, especially if they are kind of locked in their conformation, like with this T-butyl group here, react the same way. So in this case here, if we take a closer look at this, if we drew this out in like in a chair conformation, we can draw this like this, and the T-butyl group here will certainly adopt an equatorial position. This is just to make the steric interaction as small as possible. And then you have basically these two hydroxyl group. This one comes out of the plane, this one goes to the back of the plane. So in this case, both of these basically end up being equatorial. So you have OH here, and for this one here, you have OH going out here. So both of these are in equatorial positions. So equatorial, equatorial. And this allows you to actually form this, this iodate, per iodate ester if you have this conformation. So let's draw this again. O, O, and then You have the iodine over here. And from there on, basically, we follow the same mechanism as we have seen before. However, if we basically just took a similar substrate like this one, and we just changed the stereochemistry a little bit. So let's say we pick this 6-membered ring, and we just invert the stereochemistry at this T-butyl group here, and leave everything else the same. This now does not react with the periodate anymore. And the reason this does not work is that this ring now is fixed in a conformation that prevents the formation of this cyclic 5-membered ring. And if you look a little bit closer at this, if we draw this out in a chair conformation, again, this T-butyl group will adopt or force the ring in a position where this is equatorial. So this is basically forcing it into an equatorial position. And then if you take a closer look, what you'll see is that this one is coming out of the plane. So this is axial, so it points upwards. And this one goes to the back. So this is axial in this conformation too. And these two are now so far apart that they can no longer form this 5-membered ring. So that means that even though it might appear in this conformation that there's plenty of space to form this 5-membered ring, especially with the 6-membered ring conformations, you always have to make sure that you double check whether it adopts actually a chair conformation where these two alcohols are either on the same side or they are both in an equatorial position, so that they can adopt a conformation that allows the formation of this 5-membered ring. So, especially when you have 6-membered rings, make sure that you double check that this periodate ester can actually be formed sterically. All right, so this was kind of the end of the chapter on the first part of the chapter of pericyclic reactions. We want to move into the second subgroup of pericyclic reactions now. So we talked about the cycloadditions so far. Now we're going to talk about the electrocyclizations. And remember, we introduced these as reactions that proceed through a conjugated pi system and are usually within one single molecule. So the subchapter here is essentially electrocyclizations. Now, the classical example for this would be a hexatriene, for example. So if we have a system, a conjugated system that looks like this, and I'm just going to extend this a little bit by 2 methyl groups to make this a little bit clearer. If you just heat the system up, so remember, all of these reactions are formally at least reversible. So this is a 6-pi electron system. And if we just heat this, we can push the electrons around in the system. So we can say like these bonds go over here, these go over here, and these electrons move onto this side. And what we expect to get is a 6-membered ring now with 2 double bonds in this position. And it turns out that the major product from this reaction places the 2 methyl groups on the same side of the molecule. So these are going to be cis or syn with respect to each other. So at first glance, this looks like a pretty simple reaction. Whether we go forward or whether we go backward, I just swap basically the 6 pi electrons in the system around, and I go from a acyclic structure to a cyclic structure. And if I go in the reverse reaction, I go from the cyclic structure back to the starting material. Now, not everything is as simple as it appears. So if we start looking into other examples, let's say we truncate the system a little bit and we just look at a butadiene derivative, again with 2 methyl groups here. And we do the same thing. So this time it's a 4 pi system, and I just apply heat to this. I again could draw the arrows out like this. So this forms like a bond between these 2 carbon atoms, and this moves into the back here. What I get out of this is a 4-membered ring with 1 double bond. But for some strange reason now, the methyl groups are on opposite sides of the ring. So these are now trans with respect to each other. Now this is a little bit unusual because here I emphasize that both of them end up on the same side as cis, and on this model system, they end up selectively on the opposite side. So there seems to be something going on again that is correlated maybe somehow to the number of electrons in the pi system that dictates whether these functional groups at the ends of the pi system end up on the same side or on opposite sides. Now, and we have done a little bit of molecular orbital analysis already, and we're just going to extend what we used for the cycloaddition reactions to these electrocyclizations. So if we look at the molecular orbital picture of basically this last reaction, we're going to start with the shorter one, then we can draw out an energy diagram for butadiene. So this is delta energy, and we've had this so many times now. So we have the 4 pi orbitals, the 4 linear combinations of pi orbitals. The first one is, has no node. The second one has 1 node in the middle of the molecule. The third one has 2 nodes. And the last one has 3 nodes. And we know already that these pi systems, in this case, they're neutral and they're in the ground state, so they are occupied by 4 electrons, and we can just fill them in from the bottom up. So if we take a closer look now, this is going to be our highest occupied molecular orbital, and this one is going to be our lowest unoccupied molecular orbital. Now, in order to figure out like what is going on with these substituents at the ends of the pi system and how does the stereochemistry evolve over the course of the reaction, all we need to do is essentially look at the highest occupied molecular orbital. So the trick here is look at the HOMO. And all we need to do is basically, if we remember the reaction of butadiene, is basically draw out this butadiene and draw it out as the highest occupied molecular orbital. So we have our 2 methyl groups at the ends here, and then we can fill in the lobes. So it looks like this, and we just copy basically the shading from this highest occupied molecular orbital. So these 2 are shaded on the top, and these 2 here are shaded on the bottom. And this is basically just simple equivalent to the butadiene that we had in the previous case, right? Okay, so in order to form a new bond, what we have to make sure is that the bond is formed between these 2 carbon atoms, and we need to somehow find an overlap between these 2 carbon atoms that leads to a favorable interaction between these 2 orbitals, because these p orbitals are the ones that are going to form the new sigma bond. Now, one thing that I could do here is basically say like, okay, I want these two dark shaded lobes to overlap when I form the new sigma bond. So I want this one here essentially to interact with this lobe. Now, what I'll have to do to the molecule is essentially I'm going to have to rotate around this bond here. I'm just going to stretch this out a little bit. I'm going to have to rotate around this bond towards the right in order to turn this. This basically lifts this methyl up and puts it to the top. And here I'm going to have to rotate in the same direction to basically place this dark shaded lobe over here. So I have to rotate here to the right too. And that leads essentially then to a product that is a four-membered ring. I'm just going to abbreviate the double bond here in the back. But now we have the shaded lobes pointing towards the inside that form your new sigma bond. And as part of this, because we rotated both sides of this pi system towards the right, you have one methyl group pointing upwards. And if we rotate around here to the right, this methyl group is pointing downwards. So this corresponds essentially then to the product that we actually observed in this case, where one methyl group comes out of the plane and one methyl group goes behind the plane of the board, right? So these are now trans to each other. And all of this comes essentially from the rotation around this carbon-carbon bond here that places this shaded lobe in the plane and places this shaded lobe in the plane so they can form a new bond. Now, if we rotate both ends of the pi system into the same direction, so in this case, both are rotated clockwise, we call this reaction conrotatory. So con means in the same, and rotatory means the rotation in the same direction. So that's an important term that you should keep in mind. If you rotate in the same direction, we define this as conrotatory. So both sides ends of the pi system turn into the same direction. Now, just as a thought experiment, we might want to go through this. What would have happened if we had rotated in the opposite direction? So let's redraw this again. Alternative. And this is just a thought experiment right now to make sure that a little bit as a sanity check that what we're doing is actually is right and makes sense. So let's draw out our same molecule again. And we'll pick the same shading as we had before. So again, we're looking at the highest occupied molecular orbital. And again, we draw these lines out here. And then for let's say we decided for some reason to disobey this conrotatory rule and rotate both ends of the pi system in opposite directions. So let's say this side here, I'm still going to rotate clockwise. And this side here, I'm just deciding to rotate anti-clockwise. So what would you expect to come out of this? Well, if you performed this reaction that way, you would get, again, or you would be forced to draw essentially a four-membered ring, where now this rotates clockwise, so the methyl group points upwards. And this rotates anti-clockwise, so the methyl group points upwards. But if you look closer, what you essentially did now is you formed a bond, or you try to form a bond between this unshaded loop and this shaded loop here, right? If you rotate one side anti-clockwise and the other side clockwise, so that leads to an orbital overlap that looks like this, where one side here is shaded and the complementary side is shaded in the opposite direction. And if you take a closer look at this, this is something that we usually define as a sigma star bond. So it's anti-bonding interaction. So anti-bonding. So if you performed the reaction and rotated in opposite directions, and this is the rotation mode that we call disrotatory, you would get not a bond out of it, but an anti-bonding interaction between these two orbitals. So that is why this reaction does not proceed to form the structure that you would expect to come out of this. So this is why you have the selectivity that under these reaction conditions, you're not forming the syn product out of this reaction. So this is not formed. There's essentially no bond. So just to clarify this, no bond between these two. Now, so if we have a pi system, let's go back just one slide, that looks a little bit like this, where we have 4 electrons and we can analyze the highest occupied molecular orbital, and we look which direction we have to rotate these ends of the pi system to form this new sigma bond, so that a shaded lobe and a shaded lobe interact, or an unshaded lobe and an unshaded lobe interact. Then we know that in this case, for example, we have to rotate in the same direction, and we define this reaction as conrotatory. In the case where we tried the same reaction where we rotate in opposite directions, we would not get a bond between these ends of the pi system. So this is not a productive way for this reaction. Now, of course, we have not just the forward way to analyze these transformations, but due to microscopic reversibility, the reverse reaction goes through exactly the same transition state. So microscopic reversibility. So if we, for example, started out this time with cyclobutene, and let's say we have a substituent, I'm just going to pick a random label A here, and we have something down here that is B. So these are trans to each other. What happens if we performed this reaction in reverse and we just heated this up? So this is again 4 pi electrons, and based on our analysis that we had over here, no matter which direction this reaction goes, we would have to rotate the system conrotatory, right? So we can do a little bit of a more detailed analysis if we draw this out in perspective. A double bond is over here. And let's say A is going to be up here and the hydrogen on the other side. And then let's say hydrogen here and substituent B is going downward. Then we can play the same game again and extend basically these bonds a little bit, so we can define the direction in which we rotate. And let's say we rotate now clockwise on both sides because it's conrotatory. So we rotate in on both sides in a clockwise direction. Then what we get out of this is going to be the butadiene. If I rotate clockwise here, the hydrogen comes to rest in the middle, and the substituent B comes to rest here on the side. If I rotate around this bond here, clockwise, the A is pointing outside and the hydrogen points to the middle. So that means that the product of this reaction, if we just draw it out here, is going to be the ring open product that has this conformation around, around the double bonds. Now, what you also could have done is you could have decided, well, yeah, that's all fine and dandy. I want to rotate both sides, however, counterclockwise. So you could have picked an alternative way. Let's just write here alternative. And let's play through that game. Double bond here, and then A and the hydrogen down here, and hydrogen and B down here. And now I decide to rotate in the opposite direction. So I basically take this and turn it anti-clockwise, and I take this one and turn it anti-clockwise. So both of them are now conrotatory, but both rotate in the anti-clockwise direction, right? Now, if you follow this through, then you would still get a butadiene, but if you rotate anti-clockwise, the A comes now to rest in the middle. So you have A here and your hydrogen outwards. And if you rotate this anti-clockwise, the hydrogen points outwards and your B points to the center. Now, this is an allowed transformation. So these are basically both okay, just based on the orbital analysis. So they are fine. However, this one is penalized by the additional steric interaction that you build up between these two substituents. So this will be only the minor product of this reaction, whereas the one that has almost no steric interaction or very limited steric interaction between these two hydrogens, and where the substituent B and the substituent A are farthest apart from each other, is going to be the favored product. So we can draw here major product, and we call here very minor product, right? All right, so far we have only been talking about 4-pi electron systems, and just to fill out the gaps a little bit, I think it's worthwhile looking at the larger extended pi systems too. So let's just take one step further and let's look at the 6-pi system as we had in the introduction. So consider 6-pi electron system. And remember, when we started this subchapter on electrocyclizations, we had one example where we had hexatriene. And this was this system here, and we had methyl groups on both of these sides. Now, if this model holds up, we should be able to basically just analyze the molecular orbitals of the system and decide which direction this system will rotate. So we know already that the product of this reaction, if we just heat it up, is going to be the one that places the substituents on the same side. So we know that this is going to be the product, but we want to just double check whether this still works with the molecular orbital analysis that we have done previously. So what we need to do is again draw the molecular orbital diagram, and now we have 1, 2, 3, 4, 5, 6 orbitals, 6p orbitals here. This of course leads to 6 molecular orbitals. I'm just going to forget about these. The higher ones are not that relevant in this case. So again, we can fill these out. So phi 1 is going to be the one that has all on the same side. Phi 2 is going to be the one that has 1 node. So 1 node at the center. And phi 3 is going to be the one that has 2 nodes. right? So let's do the next higher one too. Let's do just for completion. All right. So again, we can look at the orbitals that are occupied in this case. So we have 6 electrons. So we have 2 here, 2 here, and 2 here. That means this is our HOMO, and this is our LUMO orbital that we have to take a closer look at. So the HOMO, the highest occupied one, is the one that is relevant for this analysis. So we can basically project these orbitals now onto the structure of the pi system that we have up here. So this would then basically look something like this. And then we have the methyl groups pointing outwards like this. So here are the p orbitals. And I basically am just going to copy the shading that we see in this phi 3 orbital. So the first one here is going to be shaded on the top. Then we have a node, so the shading drops to the bottom. And then we have a node again, and the shading goes to the top. All right, so by now you should have kind of recognized this pattern again. So what we want to do is we want to form a bond between these 2 carbon atoms here. So this is essentially the bond that we're forming in this system. So this translates essentially into this bond here. Now, how do we have to rotate around these 2 bonds in order to bring the shaded lobe and the shaded lobe on top of each other? So all we need to do is basically rotate this side here counterclockwise, and we have to rotate this side here clockwise. So you'll see that we rotate in opposite directions. So this is disrotatory. And if we do this, then basically these 2 lobes come to rest on top of each other and form the new sigma bond, so that we have a new sigma bond here. And I'm just going to draw the double bonds here in the back. But what happened with the methyl groups is that this one is now pointing upwards. And this one here, because I rotated it counterclockwise, is pointing upwards too. And these are the 2 new shaded lobes in the sigma bond. Now again, if you translate this into a structure that you see up here, they end up on the same side. So we actually have the methyl groups like this, right? So it's exactly the same structure that we had predicted here. Now, one question that you could have asked here is, well, there is another alternative to rotate this. So I could rotate this one here clockwise and this one counterclockwise. The product of that would then place the methyl groups on the bottom of the system. And this is basically the same molecule, because you have a mirror symmetry through this. So if you rotate it, it's arbitrary for you to choose whether you want to overlap the unshaded lobes or the shaded lobes in this system. So for 6 pi electron systems, it seems like that the disrotatory motion is the one that we observe experimentally. And for 4 pi electron systems, we see that the conrotatory rotation, where they rotate in the same direction, is the one that we observe experimentally. Now, those were all reactions so far that were performed under thermodynamic control. So that means that we heated the reaction, and we made sure that the energy is supplied essentially to the ground state of the molecule. Now, the same reactions also proceed under photochemical conditions. So photochemical conditions. And that means that basically what I do is I supply the energy in the form of a photon. So I irradiate essentially the reaction. Now, this changes a little bit the outcome of the reaction, but the analysis that we need to perform is exactly the same one as for the thermal reactions. So let's pick our sample again, and let's say we are looking again at the 4 pi electron system that we had previously. So this is basically our butadiene. And now instead of heating this up, we already know what the product of this is going to be. It's going to be the conrotatory product. But this time we basically just irradiate the system and we see what product comes out of this. Now we can actually predict very accurately what the stereochemistry of this product is going to be. So there are 2 possible products that we could get out of this. So one would be the one where you have the methyl groups on opposite sides, or the one where you have the methyl groups on the same side. So these are the 2 options, and we have to decide now which one under these reaction conditions is going to be the favorite product. So what we do is exactly the same thing as we did for the thermal reactions. All we need to do is look at the orbitals that are involved in this process. So we can draw out our orbital diagram again. And we fill in the shading. And if we just looked at the molecule in the ground state, so ground state, then we would have an occupation that looks a little bit like this, where basically this is now our HOMO, and this is our LUMO. However, if we run this reaction under photochemical conditions, what happens is that we excite the molecules to the first excited state. So the photon comes in and promotes one of these electrons from the highest occupied molecular orbital upwards to what is the lowest unoccupied molecular orbital. So one of these electrons gets promoted in energy, and what you get out of this then is the first excited state electronic configuration. Let's see, excited state. And you still have 2 electrons down here, but then you have 1 here, and 1 is now in what was previously this lowest unoccupied molecular orbital. And we call these single occupied molecular orbitals because there's only 1 electron in there. So we call these now the SOMO. And again, for our analysis, all we need to do is look at the orbital, the orbital with the highest energy that has at least 1 electron in there. And this is basically this one here. The next higher one, 5,4, is going to be empty. So for our analysis with under thermal conditions, we looked at this one here because that was from the ground state. In the photochemical reaction conditions, we look at this one here because that is now the highest orbital that has electrons in it. And this is the one that's going to dictate the stereochemistry. Now again, we can draw our butadiene in perspective now again. Let's draw it like this. And let's have methyl group over here, methyl group over here. And we now have to essentially draw phi-3 under the photochemical conditions. And if you look closely, it has a shaded lobe up here. Then the sign changes. It's at the bottom. It stays the same. It's at the bottom. And then at the end, again, it goes up again, right? So Now, the question that we can ask ourselves now, how do we have to rotate the system in order to make a bond, a sigma bond between these two a sigma bond between these two lobes at the end of the pi system, and you quickly realize that even though previously we did like a conrotatory motion, this time we actually have to rotate them in opposite directions to make a positive overlap between this dark shaded lobe and this dark shaded lobe. So this one, for example, we have to rotate it clockwise, and this one we have to rotate it anti-clockwise. And that essentially then gives us the product of this reaction that now the methyl group points upwards, this methyl group points upwards, and you have your new sigma bond in position here. So this is the sigma bond. And if you look closely, this now corresponds to the product that has the methyl groups on the same side, so where there's syn. So the right product from this reaction under photochemical conditions is actually the one that is opposite from the thermal conditions. So in this case, the right product here is the one where these are syn with respect to each other, and this one is the one that is not formed under these reaction conditions, right? So I know that this might be at this stage a little bit overwhelming, and many of you might be thinking, well, do I actually have to go through this quite complex involved analysis every single time that I see an electrocyclization? And the answer to that is yes, you can. It's healthy to practice that, but you don't have to. The nice thing about all these electrocyclizations is that they very well obey the rules that we have set up for them right now. And you can pick any arbitrary conjugated pi system right now. And if you know the rules, you can predict whether you have to rotate conrotatory, so both in the same direction, or if you have to rotate disrotatory in two opposite directions, right? And I'm just going to give you one example that essentially summarizes this concept with a really long extended pi system that we're going to finish today's lecture with. So what we want to is predict the product of the following electrocyclization. So predict product. And all we're given is basically just the molecule and the reaction conditions. So that's all we need to know in order to predict the product. So let's say we have an 8-membered ring here, methyl group here, and then let's do a double bond here, a double bond here, and then let's have a methyl group pointing inwards like this. Okay, so we're given that the reaction conditions are photochemical in this case, right? So what we could do now, and which would be completely legitimate, is draw again our energy diagram for the orbitals, fill in the orbitals, and find out what orbital we are actually going to be looking at when we deal with a single occupied molecular orbital, so the first excited state of the system. That's certainly fine and would work, but it's equally fast, or even a lot faster, if you just follow the rules for the electrocyclization. And these are the ones that you're probably going to have to memorize. Rules for electrocyclization. And the rules basically only depend on the reaction conditions. So all you have to know is the reaction conditions. And you have to know how many electrons are in your pi system. So in this case, it's an 8 pi system. That's all the information that you need to know. And then you basically go in this little table here that plots the number of electrons versus the reaction conditions. So let's say thermal, and we say photochemical. And then you just basically need to follow this table and see what the cyclization mode is going to be. So the nice thing is that this basically groups in the aromatic and anti-aromatic systems as previously. So you have the 4n systems, n is an integer, and you have the systems that obey the pi electron count of 4n plus 2. So the anti-aromatic and the aromatic systems. Now, if we look at the thermal reaction conditions that we discussed for both of these already, we know that the 4n system will proceed conrotatory. Conrotatory. So both of them rotate in the same direction. And the 4n plus 2 system, we had this example of cyclohexatriene, is going to be disrotatory. Right? Now, the nice thing is that for the photochemical reaction, this selectivity is just inverse. So what was thermally conrotatory is now photochemically disrotatory. And what was thermally disrotatory is now photochemically conrotatory. So they just invert essentially their selectivity. So all you need to actually memorize is basically only half of that table. You have to know that 4n under thermal conditions is going to be conrotatory, and 4n plus 2 under thermal conditions is going to be disrotatory. The only other thing that you need to remember is essentially that under photochemical conditions, this rule is just inverted, right? So it's relatively straightforward to figure this out. Okay, now that we have these rules, we can address the question that we had up here again and take a closer look at what happens with this 8 pi electron system. So let me see that I have this still on the slide. Okay, so what are we dealing with here? So we know that we have 8 pi electrons. So that means that the system is going to obey the electron count of 4n. So in the table, we are basically now in this row. So 4n electrons. We know that it's a photochemical reaction. So we are in this column. And it's basically, it tells us that this reaction will proceed favorably in a disrotatory mode. Right? So this is basically the information that we need in order to solve this much more complex system. We could have done it with the orbitals, but this is a lot quicker. All right, so all we need to do now is basically redraw our molecule. So I'm just going to draw it in a conformation so it's a little bit easier to see. Let's draw this out like this, and then double bond. Here are the other 2 double bonds, and then one was pointing inwards, and the other one was pointing outwards. And we know that we have to rotate disrotatory, so in the opposite directions at the ends of the pi system. So I can take this one and rotate it anticlockwise here. And I can take this one at this end here and rotate it clockwise. So this is now disrotatory. And then if we follow this through, this is the new sigma bond that I'm forming down here. Pi system like this. And then if I rotate this counterclockwise, the methyl group comes out of the plane. So I have the methyl group over here. And if I rotate this clockwise, then the methyl group goes behind the plane. So under photochemical reaction conditions, this is going to be the major product of the reaction. You can analyze exactly the same reaction based on this table. If you, for example, switch the conditions out, if you performed this, for example, under thermal conditions by just heating, then you would basically just drop over to this first column, and you would have to do the reaction in a conrotatory mode. And of course, this would give you a different stereochemistry at this position. Okay, this is the point where I want to end today's class. There is a lot of problems to practice that on the problem set. And I will be able to answer your questions in the office hours tomorrow morning if you have specific questions about these electrocyclizations. Next class, we're just going to jump into the last class of cheletropic reaction, pericyclic reactions, and these are going to be the sigmatropic rearrangements. And that's basically the last part of this the subchapter. And then the last two lectures are going to cover the radical reactions. All right, I will upload this lecture as soon as it's compiled, and I'll put it in the same Google Drive as all the other ones. So see you tomorrow, or see you on next Tuesday.
Professor?
Yeah?
Can I ask a quick question?
Sure, yeah.
So would you mind going back to where you were talking about?
Just wait one quick second.
Sure.
I have to make sure that I don't